Okay. Hi, everybody. If you haven't signed in on UCheck, please do it, just so we're on the safe side. So first thing first, as I said, the website's up. I'm going to be posting lectures there. So for today, this link should work. Okay, yes. So the lectures that I'm going to use, the slides I'm going to use right now are up. So you can check them out live if you feel like you need to. And I might update them because I might use the board towards the end. Then I'll add the stuff I write on the board at the end. Otherwise, I'll mostly use the website for the video recordings and the lectures and some of the high-level stuff, so that, because I don't like Quarkus, it's not very reusable. So for Quarkus, we'll just keep it for announcements, assignment instructions, project details, that kind of thing. Okay. So as for today, as I said, it's going to be a bit of a crash course in integer programming. And I know that most of you have done some form of integer programming. Some haven't done much of it and have done instead some other kind of optimization, maybe continuous. Integer programming is quite a bit different. So because much of this course, much of the research in applying machine learning to optimization has been in integer programming, we're going to give this framework some time and go deeper into it. I've asked you to read some stuff. Who here has read at least one of the chapters? Okay, any impressions from the book? Do you like the book? Easy, hard? Hard?
The material was a little bit dry, I think, because it was written sort of like a math book.
Okay, good. Yeah, it's written by a mathematician, really. So that's why, but it's not, I picked it because it's not a theoretical book. So it's not necessarily going deep into proofs or anything. Some of the other books are even more theoretical. So this one is mild in comparison. But you're right, some results require some definitions and so on and so forth. We won't be going into theory necessarily unless needed, but I'll explain kind of the main concepts and results. So feel free to interrupt with questions throughout the lecture. So I'm going to go back to this problem I showed last time, assignment problem. So machines, jobs, would like to use as few machines as possible to accomplish or execute all the jobs, and each machine has some memory and CPU capacity. Okay, so we can't violate those. This gives us a bunch of constraints. And of course, each service runs on one machine only, so we don't duplicate, we don't rerun jobs multiple times. Obviously, that's wasteful, right? We just want to execute the customer's request exactly once. So this is an assignment problem, and I showed you a mathematical formulation of that problem. We're going to come back to the issue of formulating optimization problems in the integer programming language. But the main reason I bring this back up again is because I want you to think of integer programming not as one algorithm or one type of set of equations, but more as a language for modeling decision problems. Okay, so you see something that's coming from the real world, and then some more abstract interpretation of that. This is how it actually works in practice. So the business unit will come in with some requirements. They won't even know everything they need because they might not have verbalized it or formalized it. And then the operations person will come in and say, well, actually, we haven't specified a constraint on this and that. Are there any? So on and so forth. You get into an iterative process, which gets you ultimately to a formulation that looks like this. More of the formulations we're going to see in these lectures are more like basic formulations, but they're still quite useful, quite fun. Okay, so before getting into integer programs, because we're going to focus mostly on integer linear programs, we have to define what a linear program is. So I'll interchangeably use maximization and minimization. This shouldn't bother you at all. Mostly, I'm trying to follow Woolsey in his book. So he uses mostly maximization, so I try to stick with that too. So we'd like to maximize a linear function in x subject to a bunch of constraints represented by this ax less than or equal to b. This is a system of inequalities. This is not one inequality. So you should think of this less than or equal as a element-wise less than or equal. Some people write this sign in a kind of a curved way to signify that it's not the scalar less than or equal. But that's the convex optimization notation if you've read Boyd and Vandenberg. But we'll just stick with the simpler one here. And we're going to assume that the variables are non-negative. This is not strictly necessary, but there's going to be some bounds on the constraints. It's typical in describing linear programming to have this non-negativity constraint. So two things you want to distinguish in looking at this formulation. There's two types of vectors or matrices. There's the data, which are known. These are the A, B, and C. Notice that I'm using column vectors here. So this is a bit different from the book. That's why I need to transpose the C to get the vector dot product there. So these A, B, C are known. So think of these in the assignment problem. These are the memory, the B is the memory capacity, CPU capacity. The A and the C is something like whether you're using a machine or not. So what are the machines? The A is more like something about the problem overall. That's the structure of the constraint matrix. So each row of this A matrix represents one constraint, and correspondingly there's a right-hand side, which you can think of as like some kind of capacity. So those are known, those are given. So those come from the real domain. And then there's the unknowns, or the variables, or decision variables. These are the things we're going to try to find values for, such that the objective is maximized subject to these constraints. Okay? And this is a linear program for the obvious reason that everything here is a linear function in x. Okay? There's no nonlinearities, no squares, no logs, no exponential, nothing like that. So what you need to know about linear programs is they're also highly useful. They're not as useful as integer programs because in lots of real applications, you need to restrict the x to be integer because it signifies an on-off switch in the binary case, or the number of units of a certain product that you need to accomplish, to manufacture something, right? So continuous variables don't help you with that. But it is nonetheless very highly useful tool, and you can think of basically operations research as starting primarily with the discovery of this paradigm of linear programming about 70 years ago. The other thing you need to know about them is that they're not hard to solve. So you can think of solving this problem, meaning getting an optimal x, as being solved, essentially. What we mean by that is not only that there exists a piece of code that can achieve it, because there's code that can solve any integer program given infinite time, but we don't consider integer programming to be solved. It's a harder problem. Linear programming is solved not only in the sense that you can plug it into Cplex or Gurobi or GLPK or whatever, these are names of LP solvers, and get a solution, optimal solution, but also in the computational complexity sense, that there exists an algorithm which runs in time, polynomial in basically the magnitude of the entries in A and M and N. This is good. In computer science, this means polynomial time is good. It's not exponential, okay? So it's some function that doesn't grow too quickly as the size of these matrices and the size of the entries in A grows, okay? So there's an algorithm based on something called the interior point method. I'll illustrate it very briefly at some point. That can get you an optimal solution quite quickly, okay? So we're happy with that. Anytime we have a problem that's maybe integer, we would like to write it as a linear program if we could, okay? This is a common paradigm that I know that if I can get it in this form, I can solve it. So even if I have a harder problem, if I could somehow convert it into something like this, then I could use that as like a kernel, as a subroutine. And indeed, branch and bound is going to use that idea. It's going to use linear programming as a way to get relaxations for the integer problem and solve many of them and solve the full problem as a consequence of that. Okay, so this is a linear program. You know, this shape should be quite familiar to you. Any questions? Okay. So first generalization of that is integer program. In parentheses, I have the linear, because we're still linear, and also the pure, in the sense that now I'm forcing all the x variables to be integer. Okay, it's pure because there are no continuous variables. So when I say a pure integer program, I mean this. If I say a pure binary program, I mean the variables are not integer, they're either 0 or 1. We'll see that in a sec. And if I don't say anything about linear, then linear is implied. Okay, so unless we say nonlinear explicitly, which is beyond the scope of the course, because that's an even more complicated problem, we're going to assume linear problems. That's why I have it in parentheses. This will be abbreviated as maybe IP or ILP, okay, for integer linear program. So you should be familiar with that abbreviation. What happens here is, as soon as you plug this integer in, then it's no longer a nice problem. Okay, we'll see that visually in a bit. The set of solutions is no longer, a nice continuous convex set. It's a much more complicated set. So it's harder to design algorithms for that. And if you've done computational complexity, you know what NP hardness is. One of the basic, there was 23 problems that were described by Karp when he introduced that notion of completeness 60 years ago. One of them was integer linear programming. So it's one of the canonical hard problems. In practical terms, it's more general than many other problems. So it's again, think of this as not one particular optimization problem, but a modeling framework, a language. Okay. If we have both continuous and integer variables, then we have an even more general form, which is mixed integer linear programming, or MILP, or MIP. So here, what we do is we just separate out the variables. Nothing's changing here. We're just emphasizing the fact that some of the variables are restricted to be integers, others not. These are the y's. But really, it's still a linear sum. It's just a way of renaming the variables, basically. And so think of this as the mix of linear program and pure integer linear program. You get mixed integer linear program. Same as before, data and unknowns. And in designing algorithms for these types of problems, we typically design them for the mixed case, because many real problems do have a mix of integer and continuous variables. Okay, and a special class of that is the pure 0-1 program, where variables are either 0 or 1. You might think, why do you introduce the integer version and then restrict? In reality, lots of real problems are binary or mixed binary, for the simple reason that a lot of the time you have an on-off decision. Do I buy this item or not? And also, if you have an integer variable that needs to run from 1 to 10, you don't need to create xi equals an integer in the range 1 to 10. You can create xi1, xi2, xi3, xi10. These are all binary, and it's an indicator variable. It's 1 for the corresponding integer value, and then you have a constraint which says only one of these indicator variables can be 1. This is how you enforce a binary variable representing actually an integer value. Okay? So with that expansion, which is not necessarily desirable at all times, but it's doable. So if you have basically an integer variable with a small domain, meaning the lower and upper bounds are not too far out. If you have something that should fall between 0 and 10 million, then what I just suggested is probably useless. But if you have a small range, this is actually what you would do, this kind of expansion. So binary is quite useful, and even some major players in integer programming say that in their experience in industry, most problems are really mixed binary. That's kind of the most common case. And it's also nice to illustrate things. So that's why we'll also think about this. And actually, you'll see that most of the examples of integer programs I'm going to give are going to be mainly a binary problem, but there can be many other non-binary ones. And in chapter 1 of Woolsey's book, he has a list of these applications, right? Train scheduling, production planning, etc. If you think a bit about the formulations, you'll see some of them require reasoning about integers. Okay? Any questions? And yet another class of problems is combinatorial optimization. So this is just another way of thinking about a subset of these integer or discrete problems. So think of this as yet another language. So there's the integer programming language, there's a combinatorial optimization language. A lot of the time we'll see an example. You can represent a real problem in both languages, but sometimes one is more compact or more natural, basically. So what do we say when we attack a combinatorial problem? I should note that much of research in algorithms, theoretical computer science deals with this kind of version of the same integer problems. Whereas in operations research, we deal with the integer programming formulation. And there are basically cultural differences that have led to that. In operations research, people care about solving the real problem where there might be many ugly constraints and real considerations that are not mathematically nice to describe, but that need to be enforced for the customer to be able to use a solution. Whereas in computer science, people mostly think about ideas that generalize, problems that can represent very natural classes of problems. Okay, so the focus is on essentially niceness, things that we can analyze mathematically in a kind of a effective way, which is not always the case for like an ugly integer program arising from scheduling machines in a factory to produce a certain product, okay, where there might be like many conflicting constraints, etc., that are not easy to describe. So here you see something that's very mathematically clean. There's literally like just 3 elements. You have a finite set of objects, okay? Think of this as, let's say one example is you want to decide where to build your factories. So you have a set of candidate locations, small n of them. This gives you a set n of capital N of possible locations. Associated with each such location is a certain weight or cost. For example, it costs different amounts to build a factory in Mississauga versus Scarborough. And you have a set of feasible subsets of your ground set, which is basically another way to say you have constraints. You can't do all possible combinations of the elements of your set, okay? So there's a feasible subset. This is another way of saying maybe there's like an AX less than or equal to B in the space of this problem, but here it's a bit more abstract. So this doesn't say anything about the feasible this F set being representable by a set of linear inequalities, for example. This might be like a complicated nonlinear set of constraints. And then what you want to do is you want to pick a subset of the ground set that minimizes the sum of the weights such that this set is feasible, okay? So just another way of thinking, about basically thinking about binary optimization in some sense. It's binary because for every element, you're either including it in the solution or not, okay? So this is just another way of thinking about discrete optimization. And it is mostly useful when there's some structure to the problem. So, you're not restricting yourself to the set of linear inequalities, linear objective, x greater than or equal to 0, x integer, x binary. So you can, in describing a problem, there can be more knowledge about it that can be exploited in designing an algorithm for it. So that's why we typically distinguish between combinatorial optimization in integer programming. And in fact, in the context of discourse, ML4 optimization, this is indeed a useful and a powerful distinction, because in integer programming, we tend to have solvers or algorithms which have specific structures, and we would like to learn within that. Whereas for combinatorial optimization, there are other algorithms which are effective and suitable. And typically, in integer programming, we think about optimality, so branch and bound, find the optimal solution, proving its optimality. Whereas in combinatorial optimization, you think mostly about approximation and heuristics, although you could think about exact procedures there. Maybe we'll give an example towards the end. Does this make sense? Yes? Yes?
Yeah, so can you clarify the difference between COP and discrete optimization?
Good. By the way, do you hear me in the back? Should I raise my voice or?
Yes, it's great.
It's good? Okay. Yeah, discrete optimization and combinatorial optimization, I guess you could say, so here we're getting into the subtle differences in the meanings of the words, but combinatorial is typically thinking about combinations of things, right? So when you pick S subset of n, you're picking a combination from all possible combinations of elements, whereas, discrete is perhaps a bit more general in the sense that, like, you only have discrete variables. It's not saying anything about how their values relate to each other. So maybe it's a bit more general, I would say. So, like, I think of it as discrete as being more like general integer. Here it's really binary, if you think about it, because it's almost like you represent every element in the set by an xi, and the xi is either 0 or 1, and then you take the ones. This gives you S, and then that should satisfy a bunch of constraints. Whereas discrete, when we say discrete, we're not implying anything like that. We're saying maybe something like integer general.
Okay, so discrete optimization is another term for IP. Yes.
It's closer to that, yeah. IP, when we say IP, we typically mean linear IP or ILP, which is a restriction. So I would say discrete optimization is the most general term to say optimization with integer variables, without specifying anything about the form of the constraints or the form of the objective, linear, nonlinear, etc. So I would call this whole field as more like discrete optimization. And then there's these sub-problems which are very general, and some of them are related to each other, but they all have their own specificities which make them a bit special. Okay? Good question. All right, so making things a bit more concrete, at least graphically, I'm going to take this example from Wolsey's book. So this is a pure integer program in two variables so we can visualize this in 2D, which is nice. So, so we have 4 constraints here. The first 2 are the linear inequalities. This is your ax is equal to b. You don't need to worry about greater than or equal. You can multiply everything by -1 and get it in the form from before. And then there's the non-negativity constraints, right? So this is, you need to be in this quadrant. These 2 are corresponding to, these are the hyperplanes that define, the equality versions of these, right? So if these were equals, then your solutions would need to lie on the intersection of these 2 lines. But because we have less than or equal, we need to be somewhere in this region which falls in the intersection of all of these 4 hyperplanes. Okay, hyperplanes are just generalizations of lines. But now x1 and x2 need to be integer, so actually the set of points we care about is not everything that's here, it's just the black dots that are inside the feasible region. We have this objective function, which, it's good to kind of visualize what it looks like. So it's x1 plus 0.64 x2, so you take, this is x1 on this axis. So you take this here, and then 64 here. You take the sum of them. So the direction is something like this, right? And you would like to maximize that. So a common way of visually solving a linear program, so let's forget about the integer restrictions. Our feasible set is all the points on these lines and inside their intersections, is you take your objective, which looks something like this, you put a ruler which is orthogonal, perpendicular to that, and you just slide it. You keep sliding it until you leave the feasible region. Okay? The last point you hit is going to be your optimal, is going to be an optimal solution. Okay? So you get this point in this case. So this is not very hard to see. Why? To see that this point is optimal for the linear programming relaxation. If you go down this way, what happens? You gain a bit in x1, but you lose you lose a lot in x2, right? Because this is going down very fast, right? So what I'm trying to say is, if you were to compare, say, this point with that point, what happens is you gain 1 in x1, 1 unit, but you lose 0.64 times 2 in x2, because you're going down 2 points on the x2 axis. That's 1.2, so you're losing 0.2, right? So your objective is worsening. And you could do the same reasoning on this side. So intuitively, it makes sense that this point is optimal for this. Okay. Another important fact about linear programs is when there exists an optimal solution, meaning when the problem is bounded and feasible. Okay. If the problem is unbounded, like say these two constraints, or say this constraint didn't exist, you could keep increasing the value by going all the way up. So there does not exist an optimal, so the problem does not have an optimal value. Or if the feasible region is empty, meaning it's infeasible, like let's say I tell you I want a point that's above this hyperplane and above this hyperplane, feasible region would be empty. So if neither of those two cases apply, and you have something nice like this, then there always exists some optimal solution, which is a vertex of the feasible region. So a vertex, just think of it as a point at which constraints or hyperplanes intersect. Okay, so that's a vertex. There's always going to be a vertex that's going to be optimal for a problem that has an optimal solution. Okay, so this is a very useful fact, it turns out, for one of the main algorithms of linear programming, which is called the simplex method. So if you've read the book, it's been kind of highlighted in multiple places. It's not explained in detail because the book kind of assumed knowledge of linear programming, but it's one of the basic algorithms for solving linear programming, and all it does is just a way of jumping from vertex to vertex without going through any of the points inside or any of the points on the edges between the vertices, jumping from one vertex to the other until some optimality condition is satisfied and you reach the optimal solution, and the algorithm can identify that effectively. So a lot of the time when you solve a linear program in a branch and bound tree for an integer program, you use this method, which kind of jumps between vertices. And so the fact that there always exists an optimal solution, which is a vertex, is a very important one. Okay. And the last thing I wanted to say here is that you might have a case where there are infinitely many optimal solutions. So if your objective function is like this, then if you take this ruler that I mentioned and you slide it out, then at the end you'll just coincide with this constraint. So all the points on this line will be optimal. They will have the same objective value. Okay? But in particular, there will be at least one of them which is a vertex. So what I said before still holds true. Okay? So that's the linear programming solution. It falls here. Now, what is the integer solution? The integer solution is stuck here behind me. And you can see it has nothing to do with the linear programming solution. It's nothing like, oh, it's the nearest integer point. This should already give you some intuition of why these two problems are so different and how the integer program is much harder than the linear program. Because I already told you that you can find this point efficiently in polynomial time, easily. But since the integer one falls so far, there doesn't seem to be an equivalent pattern by which if the optimal integer point was here, then maybe consistently there would be a way to round the fractional to the integer or something like that. But in general, that's not the case. So the optima of the IP and the corresponding LP relaxations could be extremely different. Okay. And if you want to convince yourself as to why this is integer optimal for this problem, you can do the same reasoning. You can just try to look at other points. You'll see that amongst all the integer points in the feasible region, this one is the only one with x1 equals to 5. Okay? So if you were to move to another point, you would necessarily need to decrease x1. What happens is, because x1 has coefficient 1 and x2 has coefficient 0.64, if you decrease x1 and increase x2, because you think that might give you a better solution, you're actually not going to get enough back from x2 to overcome the decrease by 1 unit in x1, because x2 just has a 0.64 coefficient. Okay? So this is how you convince yourself that this is going to be optimal. The other thing that's important here is that the way I describe the ruler is just there's some kind of smoothness or continuity in the space of like feasible solutions to the LP. If you move slightly, the objective function value is not going to jump dramatically. Whereas in the IP, like every one of these points can have quite a different value. So this is what makes solving integer programs hard. It's just a very discontinuous feasible region and very non-convex. I won't go into convexity here, but that's what makes IPs harder than LPs. Okay. Any questions about this example? Yes.
Hi.
Yes.
So we saw that the solution for the integer parameters could be really far away from the uniform solution. So would this be more severe in a higher dimension?
Sorry, can you repeat?
Would the distance be generally larger in the higher dimension?
Okay, that's a good question. Yeah, so let me repeat the question for the recording. So the question is, I show in this example that the IP solution can be very distant from the LP solution. Does this distance increase by a lot when we go to higher dimensional problems? So here we're only in 2 dimensions. Yes, of course, because you're going to be in higher dimensional problem, you're going to get like an exponential explosion in the number of these integer points. And so this could get even worse and worse. Another case where it gets worse is if you're in the binary case in high dimensions. That can also be pretty bad. So yes, but the one thing I would note is that this notion of the distance between the LP solution and the IP solution, or the value of the LP solution to the value of the IP solution, for some restricted classes of problems, people can prove things about this distance. So they can say that, for example, the LP relaxation value is always at most 2 times the optimal IP value, or something like that. So this is a common technique that computer scientists try to use to try to go from an easily obtainable linear programming relaxation solution to an integer solution which is of good quality, not necessarily optimal. Yeah. But in the worst case, it could be arbitrary. And there are problems where you can prove that the gap can be very large. Yes?
Just a clarification, when you mentioned that if there exists a solution, it's on a vertex, is that only for linear programming or both?
That's a great question. So this is for linear programming.
For linear.
Yeah. So the exact statement is, it's in the book, if there is an optimal, if the problem admits an optimal solution, then there exists an optimal solution which is also a vertex. So there could be other ones which are non-vertices. Yeah. But for the integer programming case, it's only a vertex if the constraints, if basically if the integer points fall exactly on the constraints. Okay, so we'll see an example of that later. These are called ideal formulations, when basically the constraints describe exactly the convex hull of the integer points. So let's say I cared only about these points, and my constraints look something like this, like a house.
Yeah.
Then if you solve that linear program, you get an integer point for free. So that's a special case of like a nice integer program. It's solved by a linear program.
So that 0.50 isn't actually a vertex?
So here it happens to be a vertex too, yeah. But what happens is this objective function, when you solve the linear program, it doesn't take you there. So had you been, let's say your objective function was more like to maximize in this direction, then you would have moved here and you would have gotten lucky and found an integer point directly. Yeah, there's no guarantee that that's gonna happen. There are special cases where you could guarantee that actually you're always gonna get an integer solution for free. And I can say one more thing about this question. So when is an integer point also a vertex, right? Let's think about the 0-1 case, just binary linear program. If you have a binary linear program, then you're working in the hypercube. So you have something like the relaxation always looks something like this. You have a line like this, line like this, line like this, line like this. So you can only be here. It's not interesting in the 2D case, but you can think about it. Think about the 3D hypercube and so on and so forth. There, now let's say you have arbitrary linear constraints, something like this, something like that. In that case, actually the optimal point is also going to be a vertex, necessarily, right? Because it's always going to fall on the intersection of the linear constraints that define x is in the 0-1 domain. So in that case, there's always going to be some objective function such that if you solve that right LP, you get the right integer point. But typically, you can't guarantee that. Okay, other questions about this example? Yes?
Have you thought about other distance measurement of the polyhedral setting? Like the distance measurement is pretty like either in or other than it doesn't necessarily apply to this polyhedral. In the solution space, not the solution value.
So you're thinking about distance between points?
Yes.
So you could obviously use things like L2, L1, Manhattan distance, those kinds of common distance metrics, right? Other objects that are related, like people try to look at the volume of the feasible region. Like, do I have a very big, expansive one, or do I have like a narrow one? So there are some ways to quantify these things, like finding the center of the feasible region. It can be useful for some algorithms as like an initialization step, things like that. So, but
What is the volume?
Can you raise your voice, please?
The volume measurement was the message, the name of the.
It's just I can't think of a method, but if you search for volume of a polytope, etc., it's a relatively well-studied type of problem. Yeah. So there are some metrics there. People look at what are typically the distances between the IP, LP opt, etc. Yeah. So there are some ways to use those things. Okay. Good. So back to formulations. I really like the approach that's described in the book. So for really a three-step approach, possibly you iterate on that. So think of this as, this is how you would get from a real problem to a mathematical optimization problem. Not necessarily an integer linear program. This is more general. So what are my decision variables? What do I control? What do I get to set the value for? Constraints, what conditions do these combinations of values for the variables need to satisfy? The objective function, what am I maximizing or minimizing? And then typically in the real world, or even in, if you're taking OR courses and you have this big, exam problem, which gives you like a production planning, some kind of industrial thing, gives you all kinds of data and confusing elements to try to see if you can figure out what's actually important or not. You write the first version of this by going through 1, 2, 3, then you realize something's missing. Like there's some constraint which you just can't model with the variables that you have. So you go back and you maybe introduce some additional variables and so on and so forth. And so this is just a general thing. We won't be doing formulations really in this course. We'll just try to solve problems that other people have already formulated, but it's good to keep these in mind. Okay. All right. So formulations, we'll look at a few canonical ones, very basic but also famous and very useful, is the assignment problem. So this is very closely related to the server problem I was using to illustrate things before. So you have n people available to carry out n jobs. Each person can carry out exactly one job, so they cannot not do anything, and they cannot do 2 jobs or more. Some individuals are better suited to particular jobs, so there's some cost. Your cost is lower if you're better for the job, and you would like to find a minimum cost assignment. So you can think of this as, because you have n jobs, n people, is just equivalent to finding, you fix the indices for the jobs, and you just find the permutation over people. Okay, so you have n factorial possible ways, okay, of assigning people to jobs, each of which will have a different objective value. You want to find the least costly one. And so in this problem, what's the data? What are the variables? Obvious what the variables are. In this formulation, we use exactly what I said. So xij is 1 if person I does job j, 0 otherwise. And then the data is really, here in this case, it's just the Cij's, the cost. So think of this as an n by n matrix. And n, the number of jobs. That's data, that's given. And then the unknowns or decision variables are the xij's. And we'd like to find good values for those that minimize this objective. This is a very general problem. So there are many variants of this with all kinds of constraints, restrictions. You might allow people to do more than one job. There might be other kinds of constraints, etc. Very highly general. And your objective might not look like this. It might, you might have a capacity on the number of you might have a capacity on the number of people you can use for the jobs, and might want to maximize the numbers of jobs you finish or something like that. So there are lots of variants on this problem. 0-1 knapsack, also very famous. You have this knapsack, this bag. You want to fit a bunch of stuff in it. Each of the stuff you fit has some weight. You cannot put too many things. There's a capacity constraint there, weight constraint, and each item has some value. And you want to maximize the value of the items you pick. So here's a bit simpler. Actually, assignment and knapsack are very related. You'd like to maximize the value again, subject to the capacity constraints. Variables are binary, so you see the strength of binary variables is already showing here. I've only had to use binary variables. And here the data is, the budget and the values, the C's, and then the variables are the SJ's, obviously. Okay, so very highly useful model. This is the single knapsack problem. You can have also multiple knapsacks. You can have more of these, each of which with a different B and a different AJ. Okay, so each item has a different weight. And then it's the same, it's just a generalization. It's called a multidimensional knapsack. Okay, so another basic problem. Does this make sense? Any questions about this? So a bit more interesting, we're going to use the combinatorial optimization version for the set covering problem. So in set covering, you have a number of regions. You want to install, say, emergency. Oh, okay, yes.
Sorry, for the NASA.
Mm-hmm.
So there's a mathematical integer programming formulation, but there's also another mathematical dynamic programming formulation. And then what do you think about the dynamic DT versus IT?
Good. So the question is, this is an integer program for knapsack. There's also a dynamic programming formulation. What's the difference? What do we think about that? So the dynamic programming formulation of knapsack, you can think of it as an algorithm to solve it. It's not just a formulation, right? It gives you a method to find an optimal solution. It takes time, pseudo-polynomial, so it's quite good if if some of the data is not too large, it's good enough, and it gives you the optimal solution. But you can think of it as just one algorithm to solve knapsack. Okay, this is a formulation which you can then solve with an integer programming solver, like with branch and bound, or maybe with some other heuristic, etc. So it's more like, this is more of like writing knapsack in the language of integer programming, whereas dynamic programming is more of like it's kind of like a method. It's closely tied to the method. Yeah, but that's a useful point. The point here is that for many of these problems, because they are classical, canonical, there are many equivalent ways of representing them. But we focus on the integer programming one again because in the real world, you don't have like a 0-1 knapsack for like an airline or for like a whatever, Amazon or whatever. You usually have a more complicated problem. When the problem gets more complicated, it becomes harder to use nice methods like dynamic programming or some simple combinatorial algorithm, etc. So then you just want to write it in this language and let a black box algorithm solve it for you. So that's really the power of integer programming there. Okay? Yeah.
Yeah. So the reason I asked the dynamic programming is because it's highly associated with reinforcement learning. So like a lot of research going to reinforcement learning.
Yes.
Is type of problem.
Yes. So yeah, that's a great point. So dynamic programming is very close to reinforcement learning. There's a natural relationship there, but it's more in the like if you write knapsack as a combinatorial optimization problem more than an integer program. So it falls more in that paradigm, rather than the integer linear programming paradigm. Yeah, it's just a different way of viewing the problem. Now, because dynamic programming, actually people have exploited that. There's some work that shows how you can, learn within dynamic programming algorithms, right? So in that case, that perspective becomes useful. So it might be something worth exploring later on. Okay. Other questions? Okay. So set covering, as the name implies, you have a set of things that you want to try to cover them. So here you have a number of regions. You want to install emergency service centers. There's a cost associated with that, and each center can only service a subset of the regions, right? So some faraway center is not going to be able to service a faraway region, and so you have that kind of constraint, and you want to pick a minimum cost set of locations to install these centers, such that all regions have at least one emergency center that can service them. Okay, so this is the combinatorial optimization formulation of that. You have the set of regions, the set M. I think I have this should be a small m, not a capital M. And then you have the set of potential centers. Okay, so these are specific locations, where you could buy a plot of land and build a center. And there's some costs which are non-negative for installing, a center in a given region. Okay, and what you want to minimize the total cost, the sum, such that when you take the union of the regions that can be serviced by an element that you picked, you get the set of all regions, meaning you've covered them. Okay, so this is set equality. So M is the set of all regions. This thing on the left is you pick a set of locations T, you iterate over them, you look at which regions they can cover, you take the union of that, you should get set equality, meaning you can service all regions. Okay, so you see the difference with the integer linear programming version of this. So this is still a full formulation, but it's more natural. There's less detail in it. It's less explicit, right? So you're using unions of sets and set equality and that kind of thing, right? It's a bit abstract. It's like nice and compact on paper. If you wanted to write this as an integer linear program, you'd get something like this, which is kind of a bit more specific but kind of uglier, right? So you can write the same problem rather than in the combinatorial optimization language. You can write it in the binary linear programming language. So xj is 1 if center j is selected, 0 otherwise. And then for each region, at least one center must service it. So aij xj greater than or equal to 1. I actually forget what the a means here, but anyway, the variables are binary, and you'd like to minimize the cost. So I think you should think of aij. So aij is 1 or 0, depending on whether the j center can service the ith region. Okay, so this is data. This is known, right? So you have this matrix of a's. Okay, so this is a integer linear programming formulation of the same problem. Also a very famous problem. Okay, questions? Okay, good. So it's 4:02. So let's take 10 until 4:10. Okay, so we're gonna resume. So we talked about this a bit before in one of the questions. There can be multiple equivalent formulations of the same integer set. So this is an example of that. What we want to model is this integer set x. So these are the 7 points we care about. They're these guys. So this is this house-shaped thing, and all three formulations are equivalent. In what sense? They're clearly not the same. So it's very different lines, and we're looking at their intersections. The intersections are not the same. What is the same though is that the set of integer points in the feasible regions of these LPs are the same. Okay? So in that way, P1, P2, P3 are equivalent formulations of the integer set x. Okay? This is a pure integer case. You could also have the same reasoning in the mixed integer case. Okay? Now all three are equivalent in that sense, but they're not. They don't subsume each other. So you can see P1 and P2 cover different areas. It's not like P2 is inside P1 or anything like that. P3 is indeed, in this case, inside both of them. And we'll see that P3 is what we call an ideal formulation. Okay? Why is that the case? Because the LP feasible region of P3 is the convex hull of the integer points. So it's ideal. It's the best formulation possible. Why? Any smaller feasible region would necessarily eliminate at least one integer point. Okay? If you have a constraint like this, you get rid of this guy, but you want to model it because it's in your set X. Okay? So why are we talking about this? Because what happens typically when you're formulating integer programs is you don't have an explicit set of points X. What you have is you have your constraints. You have your notion of what's feasible, what's possible, what you can do. But there might be many equivalent ways to write the same constraints. This gives rise to these different formulations. And some of them might be more compact than others, okay? Sometimes this compactness might come at the cost of having more constraints, okay? So it doesn't happen in this case. But let's say you're in higher dimension. You have 100 variables, 1,000 variables, etc. If you wanted to get this P3, you might have to add like many millions of constraints, for example, because you're in this high dimensional space. So if you want to, just get the integer points, you need lots of these hyperplanes together. So there might be a cost to getting the ideal formulation. Unfortunately, in practice, you don't get P3. In practice, what you write down on paper and then implement in your computer is more like P1 and P2. And depending on the problem, this is discussed very nicely in the book, you might be able to prove that one formulation is better than the other in the sense that it's a subset of it. Okay? So clearly, if one formulation yields a feasible region, which is a subset of another formulation's feasible region, we want the one with a smaller feasible region. Okay? In practical terms, why you want that is because when you solve the integer program, you're going to rely on solving linear programs. If the linear programs are very close to the ideal formulation of the integer set, then you won't have this situation where the gap is massive, for example. Okay, and then that might give you easier ways of finding the optimal integer solution. Okay, but this is to say, really, that modeling with integer programs, part of it is an art. It's not purely a science. Okay, there might be many different ways of expressing the same thing, and you might not always have the tools to prove that one way is strictly better than the other. So part of it is actually an art. So there are lots of books that discuss kind of the art of modeling. So there's one famous one, it's called the Modeling Cookbook. So it talks about various ways of expressing different kinds of constraints with combinations of integer and continuous variables, etc. So part of it is an art. Okay. Questions about equivalent formulations? All right. So getting more concrete. So here, I don't know if I can't remove my video. I'm sorry. This is just primal bound, dual bound, primal bound. Let's go to the binary linear program 0, 1. What we're doing here on this vertical line is to try to sandwich the optimal value of the problem, which we're going to go z. This is just a scalar value, 10, 15. We're going to sandwich it with two kinds of bounds, dual bounds and primal bounds, upper bounds and lower bounds. Upper bounds are obviously more optimistic, right? The optimal is 10, and I tell you the upper bound on the optimal value is 20. It means I'm giving you hope that maybe the optimal value is 20 when it's not. Okay, so optimistic, and then dual primal bounds are pessimistic. You find a solution which has value 7. It's actually not optimal, so it's kind of pessimistic in that sense. So why are we talking about this? Because at a high level, when you solve an object like this, ideally what you would like to do is find a sequence of bounds from both sides that eventually sandwich Z and converge, such that you get an upper and a lower bound which are both equal. When you get that, you've achieved optimality. This is what the branch and bound algorithm does. Okay? So now we're going to talk a bit about how you get upper and lower bounds. You get dual or upper bounds from the values of the relaxations. This should make a lot of sense because let's say we take a linear programming relaxation, we're actually looking at a larger set of possible solutions, and we're optimizing over that. So we're only going to find something that's at least as good as optimal, right? So you get dual bounds from relaxations. You enlarge the set of possible solutions. And then where do you get primal bounds or lower bounds for a maximization problem? You get them from actual integer solutions. So any integer solution which is feasible in the constraint gives you a lower bound. Why does it give you a lower bound? Again, because there could exist a better integer solution. So if I find something that has value 7, maybe there's something that has value better than 7, but I know for fact that it's at least 7, right? So the branch and bound algorithm is really the process of starting up very optimistically on the dual bound side, very pessimistically on the primal bound side, and trying to improve the two to the point where you get within epsilon. So the upper and lower bounds are very close to each other, and you declare that the best integer solution, which may be optimal or like within 0.001% of optimal, you declare that that's optimal and you stop. Okay? So we're talking about this because this is kind of what you would imagine a high-level solution strategy would look like. Okay? So we're going to make this process eventually much more concrete. So nobody's complained, but you could potentially complain about this. So what's the natural complaint? So one complaint could be, why do you care about the dual side? So I care about finding an integer optimal solution. So why don't I just seek an increasing, an increasingly, an improving sequence of integer solutions? So one by one. You need a proof of optimality. So that's really the heart of the problem. In linear programming, when you get to an optimal solution, there is a way, by strong dualities, I won't go into details here, so standard linear programming stuff. If you're an optimal point, you can check very easily that you're optimal. You can't do the same in the integer case. That's why you need this decreasing sequence of dual bounds to come so that you're able to sandwich the best integer solution and make sure that you're optimal. Okay? That's a key thing. And this should already tell you that solving a problem like this is going to be more labor intensive, because you're not focusing only strictly on this side. You need to focus on the two together. Okay? So primal and dual are terms we're going to use a lot. Questions? Okay. Good. So we talked about this. You can get dual bounds from relaxation. So this is the same toy example, two-dimensional from before. This is your feasible region. You take the LP relaxation, you solve it, you get this point. You plug that point back into the objective. What do you get? This is something like 2. This is something like, 5. So 2 and 5, you get 2 plus 0.64 times 5, that's 3.2. So you get 2 plus 3.2, that's 5.2. The optimal value is 5, right? So more optimistic, upper bound, dual bound, etc. So you get that. So this is how you get dual bounds in integer programming. Typical way is through a linear programming relaxation. There could be other ways. So I'll just we won't go into detail, but I'll give an example. You could also have an integer nonlinear program. Okay. So let's say these constraints here were not linear. They had logs and exponentials and very ugly objects there. And so the feasible region was not, the LP region was not, there was no LP region. It's essentially some funky, nonlinear region. What do people do to get bounds? They try to construct a linear approximation, some enclosing linear outer approximation, which is a relaxation of the nonlinear one. And then they solve the linear programming relaxation of that. And then you get a bound. Of course, as you relax more and more, there's higher risk of your bound being very loose, meaning it's overly optimistic. It's way too far from optimum, and you have to deal with that. So a lot of integer programming, hardcore integer programming research deals with how do you strengthen these formulations, okay? To get stronger dual bounds, okay? Questions? All right, so now let's talk about the primal bound, or the lower bound. In this case, let's use primal bound just because this problem is, for example, a minimization problem. So actually an integer solution here gives you an upper bound because we're minimizing, right? So this shouldn't confuse you. And I have a question here. Let's take the set covering problem. And the question is, can you find a feasible solution easily? Okay, can anybody construct one? Yes.
They can just find some pointer greedily.
Okay, greedily. Okay, so can you describe the algorithm?
Like we pick a point, like to cover as small as possible, and pick another one. We just iterate to
Okay,
find
good. So that's both suggests a natural algorithm for set covering. You construct a center where you can cover as many regions as possible. Now you've covered those. You don't need to worry about them. The next center you built is the one that covers the largest number of regions in the remaining set of regions. And you keep doing that until you have covered all regions, right? That will be a feasible solution at the end because by definition of the procedure, we only terminate when this constraint is satisfied, right? But we have no guarantee about the cost it's going to give us, right? So we don't know that it's going to be a minimizer. It turns out it's a good approximation. So you can prove that the cost of that solution will not be worse than factor of, I think, log of n. Okay, so there's a good guarantee that that algorithm works, but you can think of it broadly as a heuristic. It's just a natural way of doing this. Another natural way would be a greedy algorithm, which not only looks at how many regions you cover at every step, but also takes into account the cost, right? Because let's say I had, I had 5 possible regions. One of them covers, one possible set, 5 locations. Let's say one of them would cover all regions at the cost of 10 billion, but the others could jointly cover them at the cost of 1 million. Then a greedy algorithm like what Bo described would give a very costly solution, right? So a better heuristic might look at, relative cost-benefit trade-off, basically, right? How many do I cover? So how much do I get closer to satisfying the constraint relative to the cost I'm paying at every iteration? And indeed, we'll see a version of that for another problem. But this is maybe an example of, when you have a nice structure to the problem, like in the combinatorial case, you can really construct nice algorithms that exploit our understanding of, okay, this is what the constraint looks like. Actually, it's a coverage constraint. So I know that I need to cover everything, and there's a cost. So I can look at, the cost-benefit trade-off. If we were looking at the general integer linear programming formulation of this, such a structure would not be evident in and of itself, okay? So just a more general language. And so this is part of the benefit of the combinatorial optimization view of things, is that things are more, the objects that are playing to get you these solutions and these feasible regions, etc. We understand what they are, and so we can use that to get better algorithms sometimes. Okay. So let's move to knapsack. Can you find a feasible solution for knapsack greedily? So anybody has an algorithm for knapsack? Greedy algorithm for knapsack? Somebody else? Okay, Jamie.
Just put the most valuable item.
So you put the most valuable item first. That's a wrong answer. What if it violates the constraint? That doesn't sound very practical. Yes?
Maybe we calculate like how much it weighs and then we divide it by how much it costs and then we choose the ones that are
Good.
the most valuable.
Right, so one suggestion is basically based on what I said for the set covering problem, is I want to maximize the sum of the values, the weights, but I want to respect the capacity constraint. So why don't we just, while we have some budget, we look at the items which could fit within that budget, and for those, we take the ones that maximize the ratio of Cj to Aj, right? Because that means we're getting a lot of value for very little weight in the knapsack, right? So this turns out to be also a very natural heuristic for knapsack, and in practice it could work quite well. Of course, in this case, you can construct some combinations of C's and A's such that this might do, kind of really bad. So it's still a heuristic. But you can run it, and you can get a vector of values x, and this would give you a primal bound. So that's all I wanted to say, about this. And notice how in both of these cases, the heuristics are kind of combinatorial, right? They are not using really the linear programming relaxation or anything. They are using like our understanding of values and weights and covering and all these notions. Okay, so they're kind of combinatorial heuristics. Okay, and so this is what the algorithm kind of looks like. So it's a bit different from what I described. So rather than look at just cost or value to weight in the knapsack, you look at the margin. So this is flipping. So it's picking the one with the minimum ratio. So it's flip the numerator and denominator, and it looks at the marginal increase, which is just another version of a different variant of what I described, but it's also a common greedy algorithm for this type of problem. And you keep adding these items until you've either added everything or you've exhausted your knapsack capacity. Okay, questions? Okay. Now let's go back to this problem. Remember, we're minimizing the number of machines, etc. We want to assign jobs to machines. Actually, I'm going to give a simpler version of this. Let's say, so we're still trying to construct an algorithm that finds a feasible solution without any guarantee necessarily on its value. So let's say I have two processors, and these are just think of these as just the memory requirements. So this one can fit 5 units, this one can fit 3. And I have these 4 tasks, A, B, C, D, with different requirements. Okay. What I want to show here is that in this case, it's not necessarily easy to come up with an algorithm that works always, because the structure of the constraints is kind of intricate. Okay. So remember the constraints here. What are the constraints? Let's say I want to execute all 4 tasks. Okay. Subject to these capacity constraints. Now, clearly, there is a feasible solution to this. You put A and B here, C and D here. So 2 plus 1, 3, 3 plus 2, 5. Okay? This does it. But this notion might not be very easy to formalize. The constraints here are very hard. You need to do all jobs and respect simultaneously the capacity constraints. Okay, so if you have something like that does something like this, so D goes to the top one, B goes to the bottom one, A goes to the top one, you might get in this case. So you're stuck here. So this is some greedy algorithm. I didn't tell you how I assign which to which. You could tell me, oh, your rule is bad. We could try this other rule, kind of fit the smallest first or something like that. Sure, but what I'm trying to illustrate here is, because the constraints are really hard, you might, a greedy algorithm, for example, might get you in a situation like this. This is just a toy case, but this can generalize to many other cases. And so I want to say that it's not true that for all combinatorial problems, it's easy to find integer solutions, as was the case for set covering or knapsack. This might not be the case. In fact, it might be the case that finding any feasible solution is also hard. So not just a feasible solution that optimizes the linear objective function, just any feasible solution. Okay? So we shouldn't take for granted the fact that we can find an integer solution. And from a computational complexity standpoint, this is very natural. So there's an equivalence between, you can transform any optimization problem to a feasibility problem, meaning you forget about the objective and you say, just give me a point which satisfies the constraint. And so because we know optimization is hard, feasibility is hard, otherwise optimization would have been easy. So this is just a standard thing, but in many cases it might not be easy to find a feasible solution. That's all I want you to know from this example. Questions? And remember, it's not easy because of this capacity constraint and this exactly one constraint. That's why it's difficult here. Okay. You get stuck. Okay. Now, the heuristics we've been talking about, these greedy algorithms, as I said, they're all combinatorial. So they're using weights and values and the notion of covering to construct a solution. Okay? Feasibility pump is an integer programming heuristic. It has no notion of knapsack covering, weights, values, none of that stuff. All it expects is just, in this case, a binary linear program in the form minimize, what are we doing here? Let's say maximize c times x subject to ax less than or equal to b, x binary. Okay? It actually works for the mixed integer case, but this is an example in the binary domain. So this is an example of another class of algorithms which relies on integer and linear programming. So it does not use any combinatorial objects, okay, from the problem. It's a very elegant algorithm, and it works as follows. So here we're in the binary domain. So we have only 4 possible x1, x2 values. And we have a bunch of constraints that define the feasible region of the LP relaxation, so pretty standard. And we want to find an integer point. In this case, let's say I don't even care about its value. I just want to find an integer point, okay? Binary point in this case. So the feasibility pump, as you might gather from the name, is relies on this idea that I want to pump or infuse or add some kind of feasibility to some existing point, okay? So what are the 2 things that are fighting when it comes to integer programming? On the one hand, I want to satisfy the linear constraints, ax less than or equal to b. On the other hand, I want to satisfy the integrality constraints, okay? If I wanted an arbitrary integer point, I could just take any vector, 0, 1 vector, but it might not be feasible in the constraints. And if I wanted an arbitrary constraint feasible point, right, I would just solve the LP and I get a constraint feasible point, but it will not be integer necessarily. So those are the 2 things that are fighting. So the feasibility pump says I will alternate between those 2 types of points, and I will try to make the constraint feasible ones more integer, and the integer one which are not constraint feasible more constraint feasible. So that's the pumping that's happening. Yes, question. Sorry, I can't hear you.
Sorry, I was trying to understand the argument, and I got stuck in the middle. Like, what is it possible, for example, to you project to yourself to the point and then you get back to the original point that you previously?
That's a very advanced question. The short answer is yes. You could cycle. So there are some randomization strategies, some reset strategies that can avoid that. But you're right. In principle, this algorithm could get into a cycling situation. Yeah, very good question. This is the paper, by the way, and this issue is discussed in the paper at length. It's a very widely studied issue for this algorithm. Okay, so how does it work? It literally has, you can implement it if you know how to use an LP solver, you can implement this algorithm in maybe 100 lines of code, tops. So here's how it works. You solve the linear programming relaxation. Let's say our objective is to maximize CTS. You get some point. This is x bar 1. You check to see if it's integer. We know it's constraint feasible because it's a solution to the LP. Now we want to see if it's integer. Unfortunately, it's not. So the feasibility pump rounds to the nearest integer point. Very easy, just rounding. So in every dimension, just round to 1 or 0, depending on whether you're above 0.5 or below 0.5. So in this case, you're here. You get a rounding here. Now you're at x tilde 1. You check whether it's constraint feasible. Unfortunately, it's not constraint feasible. What do we do to try to make it constraint feasible? We need to project it onto the feasible region of the LP. Projection is a common step, common mathematical operator. What does it mean? It means find me the nearest point in some region to my current point. Okay? So to do this, you need to define some kind of distance metric. Okay? So let's say we're going to use something like L1 distance. So, sum of absolute differences in every dimension. Here we have only 2 dimensions. So the projection is going to look something like this. You can achieve the projection by solving some appropriate linear program. I'm not going to go into detail about that. Yes?
Excuse me, will this for the new point be the vertex, or it's not necessary?
That's a very good question. So the question is, when we project back in step 2, will we get a vertex? Indeed, you will get a vertex just because the projection problem is a linear program with the same ax less or equal to b. It's just that the objective is going to be the L1 distance between x tilde 1 and the unknown x. And so the solution will be a vertex. Yes. A very good, very important point. So now you get this vertex. Again, same thing. You check, is it integer? It's not. You round it, and here you get lucky. Because you round, you get 1, 1, and 1, 1 is both in the LP region and integer. So you declare that you found a feasible solution. Okay. Now, I haven't talked about optimization. This really didn't factor in CTX much in some sense. And there are ways to, we can study this algorithm further. It could even be a nice test bed for a course project. But basically, it cares more about finding a feasible solution. So it's very suitable for this example I showed you before, the assignment problem where a greedy algorithm would get stuck. This might possibly be more useful. The reason being, in this projection step, when you project to the nearest LP feasible point, meaning you go back into this purple region, you do it by solving a linear program. So that takes care of these hard constraints for you. Okay? We like, again, the design rationale is we like to solve the problems which we know how to solve. We know how to solve linear programs, so let's try to turn our integer thing into a linear program. Okay? So feasibility pump ends up being a very general procedure. It's not necessarily the one that's used a lot of the time in your standard bit solver. But in some cases, it can be very useful. Okay? And I'd like to refer you to the paper, which is a very nice paper. So you can learn a lot from that. Yes, question?
You just said it's not really frequently used.
Okay, so the question is, I said feasibility pump is not frequently used. What's the reason? The reason is, as noted earlier by your classmate, the issue of cycling. So you could get in a situation where you round, you project, and for some reason you round back to the same point. So you get into a cycle situation. You can get out of that by perturbing this point randomly, going to some other random point, and doing this again. But basically, the algorithm in practice sometimes has some convergence issues, and so it might take a lot of time. And there are some other heuristics, which we might have time to talk about today, which are cheaper and also effective. So there you always have this trade-off between, I might have a very good algorithm, but that takes a lot of time, and a much less effective one, which takes very short amount of time, but I can run it many times. And so maybe I can randomize it, or I can run it many times in the branch and bound tree. So you might prefer the cheaper, less successful one, just because the overall cost efficiency is better. Yes?
So I'm not trying to say anything bad about money, just out of curiosity. So
Yeah. Go ahead.
You said these are really severe issues like the speed or cycling, etc. So that what is the reason of why? I mean, this paper was done in very nice girl. So
Yes.
What's the fact that make these are really
Good. Yes, very, very good question. It actually touches on many basic things we want to learn in this course. So the question is, if the algorithm has no convergence guarantee, how come Matteo, Fred, and Andrea published this in Math Programming, which is the major journal for optimization, right? All three are, really pioneers in the field. So why do they care? So this is what I was trying to say, the distinction between the operations research perspective and the computer science perspective. These are the two dominating perspectives when it comes to optimization. The operations research, the computer science perspective wants to publish generally one of two things. Either a nice theory paper, which has very clear bounds, this approximation algorithm achieves this bound in this polynomial time, okay? Or, maybe like a more engineering-oriented paper. Here's this nice approximation algorithm. I can scale it to problems with million, billion, whatever data sets. So that's more of a engineering time, algorithm engineering kind of thing. In operations research, people care about another perspective, which is they do care about the theory, but the problems that they study are extremely hard for theory because general integer programming is very hard, right? So you have to kind of restrict and restrict to things you understand and prove something about them. But you also want to solve things in practice. So all of these people, they have either they've worked at companies or they consult with industry, or they try to solve real problems in industry. And so to do that, you need good heuristics. You need just effective algorithms that work, even when they don't have guarantees. And so when this algorithm came out, it was kind of a, just a very fresh way of approaching the primal feasibility problem of how do I find a feasible solution. And it worked really well on the benchmark of the time. So this is 2005. We'll see when we start talking about the course and the project and the data. There's a mixed integer programming library. So there was a first version of that in 2003, MIPLIB 2003. So they tested the algorithm on that. And they showed that for most instances, this algorithm can find some feasible solution and some enhancement. It can find a good quality feasible solution, okay? Now, since then, because it's been a while, there were many other developments and more effective, faster algorithms, etc. Which, back to Jamin's question, that's why maybe the feasibility pump, if you look through the documentation of some MIP solvers, you will see it is not enabled by default, or it does not run very frequently in a branch and bound procedure. But again, the motivation sometimes is something that works, that has a nice motivation, that can be implemented in an effective way, even if it doesn't have the guarantees. But I'll end this story by saying that actually there have been developments in the feasibility pump. So if you're interested in theory, I can refer you to a paper in the last couple of years where there's some improvements to how you randomize when you cycle, when you get stuck, that gives some kind of convergence guarantee, that the algorithm is finite. It might take exponential steps, but it's finite. It will not cycle. So actually, that issue has kind of been resolved. Okay? Good. Did you have a question, Bo? Oh. Okay, solved? Good. Okay. All right, so to wrap up this discussion, now we're gonna transition into branch and bound, but the point about primal dual, in practice it looks something like this. You're running, say, the branch and bound algorithm. There's the unknown opt, the z, unknown optimal value, and let's say in this case we're minimizing. The primal bound is going to be improving, right? So we're minimizing, so we're gonna keep getting better. So it's this staircase down. The dual bound is going to come from the branch and bound tree. I'll show you how that looks like. Is going to start very optimistic. It's very low, meaning you're minimizing more than you actually can, and it's going to increase. It's going to get more pessimistic, and then eventually those two will meet. And this happens in the context of integer programming in the branch and bound algorithm. You have this tree that I showed you in the first lecture, and you get these dual bounds from the LP relaxations of the nodes that you have not processed that are at the frontier of your branch and bound tree. You get some integer points, like maybe the LP solution of this node subproblem gives you an integer point. So this gives you something like a point on this blue staircase. And then as you process this tree, these two will get closer together. You'll have some tolerance. At some point they get so close that you say, the best integer solution I found is optimal, okay? So this is how the primal and dual come together eventually. Okay? Questions? The gap between them is also very useful because if you stop the solving process at any point, let's say because you run out of time, the gap gives you a guarantee. Tells you are within this % of optimal. Okay? We don't know what the optimal is, but we're definitely not worse than 10%, 20%, which is very good for practical use cases to know that you are not infinitely bad. Okay? All right, so branch and bound is kind of the star of the show ultimately. All of this is just a build-up to do branch and bound. So it combines a couple of ideas: divide and conquer and implicit enumeration. Divide and conquer is the idea that if you have a large problem, try to split it up into disjoint subsets, which together would solve the full problem. Okay. Many examples of this, machine algorithms, basic sorting, merge sort, etc. That's all divide and conquer. It's a very nice algorithmic strategy. Here it's illustrated in integer programming by saying, if I have 3 variables and I want to search in the space of all possible binary assignments, you have 2 to the power 3 of them. These are the 8 leaves of this tree. Divide and conquer suggests that rather than tackling all of them at the same time, we split the region into 2 at first. So we fix one of the variables to take the value 0 or 1, and we try to solve these 2 in parallel, right? So usually, like, that's a defining characteristic of divide and conquer. Because the problems are going to be independent, you can potentially do things independently, for example, in parallel, okay? In integer programming, it's not so easy to do that because parallelism requires some kind of balance in the difficulty of the problems. In integer programming, this subtree might be much harder to solve than this subtree, so parallelism doesn't always work, but it exists. But this is the idea of divide and conquer. Implicit enumeration is just saying, if you know you have 2 to the power 3 solutions, don't go and iterate over them, because you're going to have to iterate over an exponential number of items. So do it implicitly, not explicitly, by building out, exploring progressively, not in one shot, right? So the naive solution has no tree. The naive solution is 4x1 in 0, 1, 0, 1, 4x2 in 0, 1, 4x3 in 0, 1. Is the solution feasible in the constraints? If it is, save it, save its value, and then keep doing that. That's the naive solution. That's guaranteed every time to explore the exponentially many possible assignments, right? This solution, this divide and conquer, implicit enumeration, branch and bound, in the worst case, may have to explore everything, but in practice it does not, okay? Because as we'll see, we will use some rules that leverage the bounds to prune off some of these subproblems, such that we will not explore this tree in its fullness, okay? This is where it actually pays off. Otherwise, it would have been useless because actually you do more work. So if you have 2 to the power 3 here, if you were to just iterate over the leaves, right, that's just 2 to the power 3 work. But if you were to build this tree out fully, it's more work because it's these guys plus everything above them, right? So it only pays off really if you save a lot of them by pruning and not exploring them, okay? And one more thing, because we're going to specialize branch and bound to the integer linear programming case, branch and bound is not restricted to that. So you can have branch and bound for any combinatorial problem. So for example, you could take the set covering problem in its combinatorial formulation, not the integer linear programming formulation, and you can design a branch and bound procedure which explores the space progressively, and so on and so forth, okay? So general algorithmic strategy is not restricted to integer programming. It just happens that it works very well for integer programming, okay? But it's a general algorithmic strategy. Okay, questions about this? All right. So we're going to go through just 3 more slides on pruning, and then we'll take a break, and then we'll do an example of branch and bound, and we'll wrap it up. So we don't want to build the whole tree, so we will need some ways, some rules, to not explore parts of it. These are the pruning rules. So one of them is pruning by optimality. So let's take an example of that. Let's say we're maximizing what you're seeing here is associated with each node of the branch and bound tree is the lower and upper bound. Okay, the upper bound is going to come from the linear programming value. Okay, initially. The lower bound might come from some integer solution that you know already. You ran some heuristic. You executed the greedy knapsack heuristic that you suggested, or some kind of heuristic. So pruning by optimality is simply to say the following. Let's say I solve this node. Okay, I have 13, 27. I clearly have not solved the problem because the gap is not 0. So I branch, meaning I take one of the variables that's binary, I fix it to 0 and 1. I construct 2 child problems. This is the divide. Now I'm going to conquer. Okay? Let's say I go to this one, I solve it, I get 25, 15. Okay, also not closed, keep it. Now I move to S1. I solve the linear program. Actually, I get an integer solution. So my upper and lower bound are both 20. Okay? What does this mean? This means that there's nothing further to explore in this subtree. Why? Because if you were to branch further, you're going to restrict the space further. Okay? So you're not going to get anything better than 20. I know that I got a solution, integer solution of value 20 here. There's no way that by restricting variables further, I'm going to get a better solution. Restriction only gets me worse solutions, right? Relaxation gets me optimistic or better solutions. And so there's nothing more to do here. So I can prune this node by optimality. What have I done by doing that? I've saved myself potentially a huge subtree under this node, right? Because here, this is an abstract example, but you will have a million variables here, which means the size of the subtree here is something like 2 to the power 1 million, right? So I've saved from having to explore that, which I would have had to done had I been doing explicit enumeration, meaning iterating over every possible 0-1 assignment. One more thing happens here if you compare these two side by side, is that we've propagated some information back to the root. So the root represents basically the global lower upper bounds. Because we found an integer solution here, we update the lower bound from 13 to 20 because we're maximizing and we found something better than what we had before, which was 13, right? So we update it because we know we have 20. And also the global upper bound also gets updated to 25. Why? Because my initial upper bound, which maybe came from the LP relaxation of the problem here, had value 27. Now I solved the 2 children. Remember, this is the divide step. These 2 together partition the problem fully. There is no third problem, right? These partition the space fully. So if one of them is 20, the other is 25, right? Then clearly I cannot achieve anything better than 25, right? So I update the upper bound of the root node, the global upper bound, so to speak, to the value 25, okay? So following this step, I've narrowed down the gap from 2713 to 2520, okay? So this is similar to the plot I was showing you before. We're getting closer. We went down 1 step in the dual, up 1 step in the primal. Good. We've closed more of the gap, okay? This is how progress in branch and bound works. Question? Good, so that's pruned by optimality. I will say that this is mathematically correct. In practice, when you solve integer programs, this doesn't happen too often. Why? Because going back to the illustration of the toy 2-dimensional problem we had, typically the optimal solution of the LP relaxation is not going to be integer. Like, this is kind of rare. In practice, you don't get these nice solutions for free. Typically, you need other heuristics, like the greedy heuristic, the feasibility pump, something, to get you integer solutions, okay? So you don't want to rely on this, and that's why integer programming solvers in practice have lots of heuristics included in them. So at some point, we'll look at the skip solver for integer programming, and you'll see it implements something like 50 heuristics, right? Because it does not want to rely on getting lucky and having an LP solution which is integer, okay? So second way of bounding is a pruning by bound. Okay, so in this case, we're gonna traverse the tree in the same way, but the results are gonna be different. Obviously, this is a simulated example. So we start at the root, there's a gap, so the problem is not solved. We split it into two children. Let's say now that S2, at S2, we ran some heuristic, right? Let's say this is knapsack, we ran the greedy knapsack heuristic. Or this is set cover, we ran the greedy set cover heuristic from both. We got a solution which has value 21, okay? Now we go to S1, we solve the LP, we get two things. Let's say we get from some heuristic a solution which has value 18. This is not useful. I already have a solution which has value 21. So I can safely ignore this 18. I don't care about it. I have a better solution already. But importantly, the relaxation value of S1 is 20. 20 is lower than 21, meaning it's worse. But 20 is an upper bound on the best thing you can achieve in the sub-tree rooted at S1. Again, why? Because under S1, you're going to restrict further. As you restrict, you get worse. As you get worse, you move downwards from 20, but you're maximizing and you already have a solution which is 21. So you shouldn't waste your time in S1. You will never find an optimal solution in S1. You already have one which is 21. So now you can prune S1 and it's sub-tree by bound. This is pruning by bound. Okay? This is the most crucial one. This is the most useful one. In practice, this is what happens in practice. It highlights something which I think Woolsey does very nicely in his book, which is to highlight the fact that, again, integer solutions, feasible solutions, primal solutions, don't necessarily come just from solving the linear programming relaxation of the node. You can see how he's highlighting that by saying, when you see that you have upper and lower bound, he's implying implicitly that some heuristics are running at S2. This is actually how MIP solvers work. So it's an arsenal of techniques together. It's not just relying on branching and linear programming. Okay? So this is nicely highlighted here. And this is in practice why you would like to achieve very good primal solutions as early as possible. The earlier you have your 21, the sooner you can prune out more nodes of this tree. Because this is a very simple case. In practice, you're going to have a very nasty tree with hundreds, thousands of nodes. So as soon as you have a better integer solution, you can go through the ones that have not been explored, just like how we went through S1, and prune out many of them. Just get rid of them. And this saves you potentially a massive amount of time. Okay? So this is by far the most useful or most practically occurring kind of pruning. And of course, it applies only to feasible problems. If you have an infeasible problem, which in some kind of peculiar applications might be the case. In practice, like if you think about an industrial problem, you're not going to have generally an infeasible problem. You're going to have a feasible problem because you know you can do something. But if you're infeasible, you don't have these bounds. You just have the LP bounds. And then it's a different kind of, it's really, you can solve it with the same technique, but for example, you would not prune by bound there. You would only prune by, not by optimality, but by getting infeasible LPs. Okay, and so yes, that's not mentioned explicitly in the book, but you could also prune. So pruning by optimality can also mean pruning by infeasibility. Like if you, let's say you're further down the tree, you've restricted too much, you might get an empty LP region, in which case you run the LP solver, you get no solution. It declares the problem infeasible. You can also eliminate the node, prune it, because if it's infeasible, restricting variables further in its subtree is not going to make you feasible. It's only going to make you more infeasible, so to speak. So another way of pruning by optimality is pruning by infeasibility, essentially. Okay. Now in this case, last, you get into something that also happens a lot in practice, which is sometimes pruning is not possible. Like you need to wait longer before you prune. So this is an example. You have a primal bound of 40, a dual bound of 40. You have no integer solution because your heuristics didn't return anything. You branch. You get also don't have an integer solution here. You get 37 upper bound. and then you go to S1, you get a solution of 13. You can't prune anything here. You can't prune any of these two nodes. Why? The solution of 13 here is worse than 37. So the bound here is more optimistic still. So there could be something which is better than 13, worse than 37. So you can't eliminate this node, right? And you also can't eliminate this node because there's a gap between 13 and 24. So there might actually be a solution in S1 subtree which has value up to 24, right? So you can't prune anything. All you do is you update your global bounds. You say, actually, I now have a feasible solution. Its value is 13, so my global lower bound is 13. And also, my most optimistic upper bound is 37. So you take the max of the nodes that are on the frontier, right? The leaves of your current tree. Max of 37 and 24 is 37. Global upper bound is 37. You can't prune anything. Yes?
So does some of the IP server has kind of function of trying to find the feasible solution in 3 seconds, and find just proceeds?
In few seconds?
Yeah, I don't know how they work, but you said there's a cases where the heuristic does not find it.
Yeah, so that's a good question. So the question is, do the MIP solvers have some kind of way of saying, okay, run a heuristic for a restricted amount of time and try to find some integer solution quickly, right? Yes, that is the name of the game. So all they're trying to do is balance the trade-off between running heuristics, which increases the chance of finding an integer solution, and spending time running those heuristics where their chance of succeeding might be very low. So you have this very intricate trade-off, right? I could run heuristics all day, change the random seed, look at subsets of variables, try to do all kinds of things. But if I spend too much time on that, it takes my mind off actually exploring the branch and bound tree. And so this trade-off is actually a research topic. Like, how do you manage this trade-off? But yes, the MIP solvers have ways of saying, like, they might have ways of saying, like, if I have not found any feasible solution in a very long time, maybe I should intensify, run more heuristics now. But these are the things where machine learning can potentially play a big role in trying to, based on a set of instances, try to see what kind of heuristics work better, or how much time should I give this heuristic versus that heuristic. And people have actually worked on this kind of problem. Yeah. Good question. Okay. Good. All right, so we're going to take one more break for 10 minutes until 5:20, and then we'll do one last run over branch and bound, and we'll call it a day. Question?
Yes, so for those kind of machine learning to decide which heuristic is better than the other, isn't that just a really simple machine learning regression model? Like, probably gonna be linear regression. Like, if there is special about, like, what's the special about the algorithm?
Yeah, you could. I mean, it depends on which level you're deciding. So one way to think about it is you could say, okay, I want to decide at every node which heuristic I should run. Okay, I have 5 heuristics. I want to run ideally a small number of them, right? And I want to pick the ones which are more likely to find a solution in this node. Okay, so the way you could do that is you could formulate that as some kind of classification problem. So you have some features of the node, and you have a model for every heuristic, which spits out the probability of success based on a database of historical runs of this heuristic. Okay? You could build a classifier like that. You could also build some kind of regression model, for example, which models the running time of the heuristic as a function of the features of the nodes. So there are multiple ways you could potentially look at that. Yeah?
My question is actually like those kind of machine learning. I think it's the linear regression method itself is good enough. And it's more about the feature instead of the model, machine learning model, or that heuristics.
So linear regression. What are your inputs? What are you trying to predict?
Probably some known information or some states.
And you're trying to predict what?
Which heuristic available in your software library that you should enable.
Right. But that's more of a classification problem, right? Yeah. So that's one natural formulation. That something like that has been done. But there are other ways of approaching the problem. Yeah. Okay. Good. Let's take that. Okay, welcome back. So we're almost done. We're going to try to do one example of branch and bound, concrete example. Before that, let's go through the actual algorithm with this nice flow chart. So this is from the book. In addition, I've annotated some of these main steps. Using blue for pruning, red for decisions you have to make, selecting a node from the set of nodes in the tree, or selecting which variable you should branch on, and black and gray for kind of fixed steps, solving the LP or terminating, and green for primal heuristics. Okay, so we'll go through this flow chart, top to bottom. So you start with an initial problem. Reformulation P just means you have the something like the whatever set of constraints you're using to represent the problem. You have a list. This is this list that's mentioned here. It's just a list of nodes. It's a list of problems which you are yet to solve. So initially, it's the whole problem, which you have one node. You put that on the list. These steps we'll do before we enter this loop, right? Because you notice this is a loop here. We're maximizing, so initially we don't have an integer solution. So we initialize our lower bound to be negative infinity. That's the worst possible. And our incumbent, this is a word we use for the currently best integer solution. The incumbent x star is void, doesn't exist. We would like to have an x star. So what we do is we run some primal heuristics, maybe more than one, not just one. And if we do find an integer solution, then we update our lower bound to the value of that solution, z sub h, and we update our incumbent solution to be that vector, xh. Okay? So if we get that, that's really nice because you can only compute the gap if you have both an upper and a lower bound. Usually getting an upper bound is easy because you solve the linear programming relaxation, you get that. But a lower bound needs an integer solution. So until you have a lower bound, you don't have a gap. You don't know how far apart the two are. That's why typically solvers, and you'll see that if you've run any, and when you run any, you'll see that they spend like significant amount of time processing the first node, the root node. Why? Because they're running lots of heavy machinery there to try to tighten the formulations or find a good feasible solution very early on. So this step here is there for a reason, just to emphasize that you actually run primal heuristics early on. Now, remember you have a list of nodes or problems. Initially it just has the root node, which represents the full problem. If the list is empty, you're done. That's the termination criterion. Of course, if your primal heuristic, if your primal value, so here you're not going to be, you're going to have at least one node, which is just the root node. So the list is not empty. No. You remove some problem from the list. Initially, again, you have one, so you only have one problem to remove. You solve the relaxation. This gives you this dual bound, which is the upper bound. You see Z bar. Okay. The I indexes just the number of the subproblem. So when it's the root node, it's the I is 0, right? S0, the initial LP relaxation of the whole integer program. If your bound, your dual bound, is smaller or worse than your integer bound, so if your dual bound is worse than your primal bound, okay? Meaning your supposedly optimistic bound is actually worse than the best integer you've seen, then you can prune by bound, okay? Why? Again, there's no way that this subtree is going to have something better if its relaxation value is already worse than the best integer that we have, okay? So same rule as 3 slides ago. So if you prune by bound, then we're done with this node. Go this way, iterate back, go process another item from the list, another node in this set of nodes. If we don't prune by bound, we still need to solve the LP relaxation. Okay, so one thing I missed here is the following, because it's not clear from notation. For any node, except the root node, you can initialize the upper bound to be the parent's LP value. Okay, so for any node in the tree, the parent is going to be at least as optimistic, because going down from the parent to the child, you're going to restrict by fixing a variable to 0 or 1, or adding, focusing on some sub-region. So you're only going to restrict further. So the parent can only be more optimistic, okay? So initially, when you create the node, you set a dual bound for that node, which is the parent's LP bound. You can do that because you have solved the parent's relaxation. Otherwise, you would not have created the child, okay? So for the parent, you have the relaxation value set to that. So now, if we don't prune by bound, now we actually solve the child's LP relaxation. This gives us an updated upper bound, which is the LP value of that relaxation. This also gives us, obviously, a solution, which is this XI-LP, the LP solution. If the problem turned out to be infeasible, meaning the PI, the feasible region, is empty, I mentioned this before, you can prune by infeasibility. There's nothing to do. If a subproblem is infeasible, restricting it further is not going to make it feasible, so you can prune. If it's not infeasible, then you check the prune by bound condition again, okay? Why do I check it twice, here and here again? Because before I solve the LP, I initialize the node's dual bound to be its parent's LP relaxation value. If I can prune it by bound here, why would I wait until here to prune it? Because for me to get here, I need to solve the LP relaxation. That takes time. So if I can prune earlier, I will prune earlier. Okay, that's why you have redundancy here. You have 2 prune by bound. Okay. If you can prove by bound, you go back, you process another node. If you can't prove by bound, you check if your LP solution is integer. Okay. If it's integer, you check to see if it's better than the best integer you've seen so far. If it is, you update your incumbent to that. And now you prune by optimality, right? Again, because we found an integer solution at this node, further restricting is not going to help us at all, right? Because further restricting only makes things worse. So if you found an integer solution in the LP, if the LP solution is integer, you can prune by optimality. And if it's better than the best solution you've seen so far or your incumbent, then you update that. Otherwise, you don't do anything. You don't update it. You already have a better integer solution. Last, if all of these fail, meaning you've not pruned by bound, you've not pruned by infeasibility, you've not pruned by optimality, this node still exists, and by the divide and conquer principle, we need to divide. Okay? So this is where the branching variable selection step happens. We return 2 subproblems, SI1 and SI2, which have 2 formulations which restrict the region further. So how do they restrict that? Very simple. In the binary case, you take some variable, which is fractional in the LP of that node, and you force it to be 0 in one child, 1 in the other. If you're in a general integer problem, let's say you take some variable xi, it has value 5.4. In one child, we restrict it to be less than or equal to 5. In the other, greater than or equal to 6. And we have split the integer domain into 2 problems, which together maintain the completeness, right? Because we know this variable has to be integer, so it's not going to be 5.4 or anything between 5 and 6. So we restrict it. We'll see visually, graphically, how that looks like. This creates 2 new problems, which what are we going to do with them? We're going to add them to this list. Okay? So the list grows by at most 2 at every step, because you create, it's a binary tree. You return those 2 children, you add them to the list, you go back to the step. At some point, you will have pruned so many nodes by all these different rules that your list is going to be empty. When your list is empty, you're optimal. Okay? And then you terminate. That's it. So this is the complete branch and bound procedure, just vanilla procedure. There's all kinds of implementation things you can do, but this is the basic algorithm. Okay? So I'd like us all maybe to just take a look for a minute and make sure it makes sense. If there's something in the notation that doesn't make sense to you, you can also ask me about that. Some people said some of the notation was new or unfamiliar. So take a second to look at it. Let me know if you have questions. Yes?
I just have a question on the list.
Mm-hmm.
So the lists are just the nodes you're solving?
So it's the nodes that are outstanding,
Okay.
which are the nodes which you have not processed yet. You've only created them in the step when you process their parent,
Yeah.
but you haven't processed them. Why does this happen? Because at every step, you have 2 children.
Yeah.
But after that, you take only 1. So you grow by 2, you process 1. So your processing rate is half as your creation rate. And so you always have you grow by 2, you take 1, you grow by 2, you take 1. So you always have a growing list, right? Until at some point you start pruning fast. So you actually see that when you solve integer programs, it prints out the logs, and you will see number of nodes you've processed versus number of nodes you've created. And at first you're creating much more than you're solving, but at some point the pruning intensifies, and then you're pruning very quickly, and you can see that the list basically shrinks very quickly as your bounds get stronger. Yes?
So, when you have large size problem, how do you know the variable is really integer? Yes, you solve it by linear realization, and then this floating point.
Okay, good question. So the question is, are integers really integers? Okay. In theory, conceptually, it's not a problem. But when you solve anything numerical on a computer, right, there's a limits to the number of digits you're going to use to represent real numbers. So in fact, you cannot represent, you don't represent real number existing fully because you have some finite number of bits that you're representing them. So really, you're just representing a discrete subset of all possible real numbers. So you get into something which is called floating point errors, right? So there are 2 answers to this question. The first answer is you kind of ignore it. So you don't really think about that too much. So there's some numerical preprocessing that the solvers do, but you basically don't worry about it. Now, there's a line of research which is called exact integer programming, which actually does not use the same floating point arithmetic. So it does some other additional work, more expensive, makes the algorithm much slower, that can guarantee exactness. But you need some other kind of machinery. So I'm not an expert on that topic. But it's a whole other thing. So if you search for exact integer programming, there's actually a solver, there's code you can run, which is exact. But indeed, in practice, you could get into a nasty situation where you find some solution, the solver declares it to be optimal, but you do some checks and it's actually not feasible by some small distance from the feasible region, but it could happen for some nasty numerical reason. So these things happen. Just maybe not super common. Yeah. So in general, I don't worry. I don't lose any sleep over it. Personally. Other questions? Branch and bound. Okay. I mean, yeah. Basically, you should be able to describe this algorithm in your sleep to like somebody who knows nothing about optimization. So it's a very useful algorithm. So try to get to that stage soon enough. It will be very useful for the course, even if your project has to do with a heuristic and not necessarily with branch and bound, which we're going to talk about that, and you don't need to do something within branch and bound, but in general, it's very highly useful. Okay, good. Now what I'm going to try to do is yes. Is it related to this? Yeah, you can ask. Can you raise your voice, sorry? Implementation?
Yeah.
Okay, so the question is, in the project, if you're doing something with branch and bound, you have to implement it, right? Yeah. No, that's a fair question. In general, you will not implement it because it's more complicated than this, right? This is an abstract representation of the algorithm. In practice, you have to worry about lots of things, like how do you manage this number of nodes? How do you store them efficiently when there's so many of them? How do you solve the linear programs efficiently from node to node? Those are actually discussed in chapter 7 in the book. All those things. So solvers can do those for us. And so we will try to learn at a bit of a higher level and try to reuse the typical branch and bound codes that are out there. Yeah. But I can say also that if there could be a project which has to do with branch and bound, not for a integer linear program, like a branch and bound for a combinatorial program. In that case, instead of, the only thing that changes really is instead of solving an LP relaxation, you would have some other kind of relaxation, some combinatorial relaxation of the problem. Why? Because the concept of relaxation is just to say, I enlarge the feasible region in such a way that I can solve the relaxation efficiently. That's everything you need for a relaxation. And so you could have some graph problem, some specific problem, knapsack, cassette cover, etc. And you can have your own combinatorial relaxation. Actually, some of them are discussed in the book. And you just plug that in. It's a very generic procedure. And then you apply the same thing. You build a binary tree, etc. Another generalization is you don't need to build a binary tree. If you have an integer problem, you could not build a binary tree. Let's say each variable takes one of 5 values, then you can build 5 varied trees, which means every node has 5 children. Xi equals 1 equals 2 equals 3 equals 4 equals 5. So you could build a tree which looks more like this, right? Very wide. But that's typically not preferred. People like the binary tree structure. So for a project, if you're doing branch and bound for any kind of integer linear programming, 99% of the time, I would say, we will reuse some solver and manipulate them because they have some interface, programming interface that allows that. If you're doing branch and bound for some other class of combinatorial problems, you might implement your own basic branch and bound. Is that good?
Yeah, that's
okay, good. Other questions? Yes.
I'm sorry I missed it. Can you please explain again why you have the provide bound for the linear?
Good. Yes. My bad. So here's why. So let's start from this step. I create the 2 subproblems, the children. Okay. I have not solved their LP relaxations yet. Why? Because I have not processed them yet off the list. So I have not gotten to this step. Okay. Nonetheless, I would like to associate some upper bound with them, some value which I know is the best that you could achieve in that subtree. Okay. I do have one such value which I get for free from their parent, which is where I branched from, which is the parent's LP value. So first, you need to be convinced that I do have the parent's LP value, and that's because for me to get to this step, I've done this one. Okay. So I have the parent's dual bound or upper bound. Why is that a valid upper bound on the child? Let's take a binary case. To create the children, I take some variable xi and I fix it to 0 and 1. What's that do? It's further restricting the feasible region. So you cannot possibly hope for a solution which is better than the parents. Because in the parent, it could be that the same variable xi had value 0.5, and now I've restricted to 0 or 1. So there's no way I'm going to do better than that. Okay? Therefore, z bar I, which is the parent's LP value, is a valid dual bound or upper bound to both of the children. So I initialize it with that value. So now where does that value become useful? That value becomes useful when I add this child to the list, and maybe later on I process it off the list for whatever reason. But in the meantime, I got some integer solution which is actually has higher value than that bound. Because I have that bound associated with the node, I can prune it by bound immediately. I don't even need to go to the step where I solve the LP relaxation, because I know the integer solution is already better than the bound. That bound's only going to get worse.
Oh, okay, so that primal bound on that, you continuously updating that.
Yes,
on other nodes.
exactly, precisely, yes. So some work has happened, and it turns out to be useful, and I would like to save. So had I not saved or initialized the upper bound here, I wouldn't be able to do this. I would solve the LP, and then I would discover redundant information, which is that this is not going to be as good as the best integer, and then you prune.
Yeah, I was confused about if the child couldn't pass that first pruning rule. I didn't understand how the parent could pass that first pruning rule, but I understand.
Yeah, good. Does it make sense to everybody? Yeah. Yes.
Could you give some input of why? I mean, the branch bound itself is by itself is okay, but if you think about part, the decision tree in terms of algorithm, why the decision tree sort of algorithm cannot be replaced? I mean, like the branch bound for IT cannot be replaced by part.
The branch and bound for an IP cannot be replaced by what?
Decision tree.
Decision tree.
For example, part. Something similar.
So the you're thinking about the CART algorithm for greedily constructing a decision tree for like classification. So you can. So they are conceptually very different. The branch and bound tree is just a representation for how you search in this integer or mixed integer space. The decision tree returned by a decision tree algorithm like CART is the actual solution. It's the actual, like it's the x vector basically. You can think of it that way. So the two are conceptually serve very different purposes. But if I wanted to get your question closer to this, is like, why would I not kind Right. So CART is like some kind of greedy algorithm. So a greedy algorithm in the case of branch and bound might mean that it essentially relates to how you select the nodes from the list. So you could select those nodes greedily, meaning you do a depth first search. You always select the node which is deepest in the tree, or something like that. Or you select the node which is most optimistic. So these kinds of decisions as to how you explore the tree, that's why I have these two important steps, node selection and branching variable selection in red. Those are the two where you could have some different search strategies. That some of them could be greedy like in CART. Yeah, but the two are conceptually very different.
Yes, and also the information that
It's not that the CART will fail, it's just that it doesn't, it's serving a different purpose. CART is just a greedy construction heuristic for a decision tree. Right, but in CART, you're trying to get a tree. Here, we're not trying to get a tree. The tree is just a way in which we explore. So eventually we want to find the globally optimal solution. So we want to close off this list, right? So conceptually, they are trying to do different things. You can think of CART as just a primal heuristic for an integer program, which represents finding a decision tree with maximum accuracy on a training set. You see? So conceptually, they're at different levels. Yeah. Okay, good. All right. So, okay, so I think we're out of time, so I'm not going to do, this absolves me from doing the example on the board, which is nice. Because that was going to be painful, but because it's a long example. That's not because I'm bored. Okay, so I'm looking at the. Okay, good. This was the example I wanted to give. I'll just go through it very quickly. So the problem looks something like this. It's an integer problem. Don't worry about the dashed lines for now. Just look at the full lines. These are the constraints. So that's the problem. The dashed lines you're going to see are these constraints that result from restricting the problem further. Okay. So something like you branch on x1, so you restrict to less than or equal to 2, greater than or equal to 3. You branch on x2, you restrict to less than or equal to 0, which means equal to 0, greater than or equal to 1. Those essentially split up this bigger feasible region. Okay? The branch and bound tree for this problem looks something like this. If you could go through the example on your own to make sure you understand it, that'd be great. So we start at the root. We solve the LP relaxation. We have no integer solution. You get this 59/7 value for the dual bound, the upper bound. You pick some variable to branch on, in this case x1. You add these constraints, less than or equal to 2, greater than or equal to 3. Okay? Here they are. These are these guys. So we started with this full region. Now when we branched, we restricted to this region, which goes something like this, and this other region, which in this case basically happens to be infeasible, happens to be empty. Because if I do x1 greater than or equal to 3, you can see here, I am outside of the intersection of the original constraints. Okay, so this guy is infeasible. There's nothing there. So this is our initial branching, and so you get negative infinity here, and you boom by infeasibility. There's nothing to do here. On the other side, there is something to do. The region is not empty. You solve it, you get some fractional LP solution. In particular, when you restrict here, the objective, I think, is something like this. So you get this as the optimal solution, okay? This is going to be your LP optimum solution. Now, what do? You branch. Why do you not? You could branch on. So you could branch on either x1 or x2. But if you look at this solution, you'll see x1 is already integer. It's already 2. So there's no point saying x1, less than or equal to 2. You're gonna reproduce the same problem in the child because it's already integer. So you branch only on fractional variables. There's only 2 variables in this problem. x2 is the only fractional one. So you branch on x2. How do you branch on x2? x2 is half, right? So you're gonna do less than or equal to 0, greater than or equal to 1. Less than or equal to 0, we already have greater than or equal to 0. So it's gonna be x2 equals 0 essentially. So you have a region in which x2 is equal to 0. And in the other one, greater than or equal to 1. In the other one, this is going to be the LP optimum. And so you get 2 children that look like this. And in the x2 equals 0, you just get 1 point. And in the x2 greater than or equal to 1, you get an integer solution. Why? Because if you look at this point, so you've added this constraint. So you've added this constraint in the first step of the branch and bound from the root, and this constraint in the second step. This gives you this nice square region here. your objective is in this direction, you go as far as you can because you're maximizing, you get this point, it's an integer point, hooray, you can prove by optimality. And you're gonna be done because in the other child, what do we have? We have x2 equals to 0, and we have x1 less than or equal to 2. So you're gonna be along this line, and you're gonna get a worse solution. So you're gonna get a solution that's 6. Here we have a 7. So if you get this one, if you process this node first, you get a 7, then you process this, you realize 6 is gonna be worse, and you're done. So the ordering doesn't matter. Okay, so that's a worked out example. If you're still confused about branch and bound, I recommend going through it. And we'll meet next time. You'll hear from me in terms of reading and assignment 1 update. Okay? Any questions? I'll probably be outside just so that the instructor can set up. Okay? Thanks, everybody.